Welcome. Good morning, good afternoon. Welcome to everyone to our 5th year of the Aviation Reimagined webinar series hosted by Griffith University in Australia. This is our 2nd webinar this year of a 3-part series running every Thursday afternoon at 3 p.m. Brisbane time. We will put a link in the chat function soon for anyone who would like to watch last week's session or any session from the previous 4 years. Griffith University acknowledges the traditional custodians of the land on which we live and are located for this meeting today. We pay respect to elders, past and present, extending that respect to all Aboriginal and Torres Strait Islander people. My name is Susanna Becken. I'm a professor of sustainable tourism, and I'm facilitating today's session with Professor Tim Riley from Griffith Aviation. Now, last week we looked at decarbonizing aviation in context. We looked at the economic and regulation issues, and today we have an opportunity to explore some of the environmental impacts, for example, contrails, on-the-ground climate risks and adaptation needs, and of course pathways for future technologies, in particular hydrogen. We're very cognizant of the global need to decarbonize as quickly as possible and reach net zero emissions by 2050. And last week, again, we were reminded of the immense task and the tight timelines due to the shrinking carbon budget. Today, we have 3 presentations because of time zone issues, our first speaker will leave us after his presentation. That's why today we do it slightly differently. We have a small Q&A after the first presentation, and then we have, as usual, our bigger Q&A session at the end. So please, again, as always, keep posting questions in the Q&A session. Speakers will do their best to answer them during the event, and we have material for a good discussion at the end. Now, it's my great pleasure to introduce our first speaker and welcome Alejandro Bloch, who's from IATA based in Montreal. And thank you so much for staying up late and joining us. We're really pleased to have you here and learn from your expertise. Alejandro is the manager for new energies and technologies at IATA, which involves understanding the energy transition of aviation, moving from conventional jet fuel to safe hydrogen batteries. And as such, Alejandro was the leader of the IATA Net Zero Roadmap initiative. Prior to joining IATA, Alejandro led several technology and sustainability positions in organizations like ICAO, Airports Council International, and the Aerospace Technology Institute, where he led the delivery of the aerospace technology strategy for the UK. Today, Alejandro will focus on hydrogen as one path to deliver aviation's climate goals. Again, please, if you have questions for Alejandro, just post them during the presentation. And now I hand over to you. Alejandro, the floor is yours.
Thank you, Susanna, and hello, good afternoon, good morning, and good evening to everyone. Thank you also for Emma for doing this introduction, and Susanna for introducing me. Yes, we've got about 20 minutes to talk about this, so I'll get started. What I will talk about today is hydrogen for aviation. So I'll cover some basics on the fuel. Why are we looking at hydrogen? How is it different to kerosene or SAF? Very, very high level. Then a few comments on the aircraft and what is the interest that we have as IATA or some of the work that we're doing. Then the airport, and then a quick note on the state of the industry and what's happening around other sectors. So I'm also very pleased to share this the floor after with Professor Keith Chan and with Rachel Barbridge. It's quite an honor to share this slot with you both. So let's get started. And this, for some of you, might be quite obvious, but I thought it was a nice way to start. Let's talk first about conventional aviation fuel or kerosene. So, as you may know, kerosene has emissions associated to both the combustion and the manufacture, if you like, of kerosene. So as we extract oil from the ground and then refine that oil and process it into aviation jet fuel and then transport it to the airport and then burn it, there are emissions associated to all of those processes. So about 84% of the emissions on average happen during the combustion of the fuel, and the rest happen before. So before we even burn the fuel on the aircraft, there will be emissions associated to it. So I've put an example there, about 14 point something grams of CO2 per megajoule happen before, and about 74 grams of CO2 per megajoule happen during the combustion. And on the right-hand side, you can see a little graph that shows you the sort of fuel extraction emissions and the CO2 release during flight and how they add up to a total. What happens with SAF is, and I'm showing here just one particular case of SAF for a particular feedstock. So the CO2 gets absorbed by, let's say, a plant or a carbon capture facility or something. And then that CO2 creates, in this case, an oil that gets refined into jet fuel. And in this particular case, the emissions associated to the process of the fuel are a little bit higher than kerosene. You can see 22 grams instead of 14, but the emissions in flight get fully compensated by the emissions that were absorbed. So you can see on the right-hand side, the sort of feedstock at the beginning is a negative emission, and then we emit a little bit on processing those feedstocks, and then we release emissions in flight. So hydrogen is from an emission accounting perspective, is a little bit more elegant because we break the carbon chain. That's a term I like to use. So we have no carbon at all during the process if we do it with renewable energy. So in this case, we have renewable energy that has a specific footprint associated to it. It's not carbon zero. So in this case, it's about 10 grams of CO2 per megajoule. So that's quite a clean grid coming from renewable energy. And then from electrolysis, water plus renewable energy, we make the hydrogen. And then the only emissions associated to it, the only carbon emissions, are those associated to the transportation and residual emissions on the renewable energy. So of course, it's not only about CO2, there are non-CO2 effects, and Keith will speak about that in the following presentation. But it's just to provide a representation of how is hydrogen different to SAF and kerosene from an emissions perspective. Now, IATA has developed a net zero roadmap. So we identified 130 independent milestones of things that need to happen for us to get to net zero CO2 by 2050. And this depends on us replacing conventional fossil fuels by renewable alternatives. So you can see in this graph or projection of how we need things to happen, where today we use about 100% of fossil fuels, and that phases down to almost 0 or 6% by 2050. And hydrogen aircraft start appearing around the 2037 timeframe, more or less, and start occupying a larger share up to 2050. Now, this is our sort of mid scenario. We do have scenarios that are more aggressive and also ones which are more conservative, and this depends on how much financing, how much policy, how much support we get to accelerate these things. Now I'll speak a little bit about the aircraft. So hydrogen can be used in two ways. It can be used like conventional jet fuel, so it can be combusted in a jet engine or a turbofan engine. So the energy gets extracted in thermal way. And here you have a little diagram of an aircraft designed by the Aerospace Technology Institute in the UK, where the hydrogen is stored in these green tanks and then transferred to the jet fuel and then combusted. And at the bottom, there's a schematic of a test rig, which I actually visited from Cranfield University, where they are testing a little section of the combustors that they're actually burning hydrogen and seeing the properties and relight ignition and so on. And Rolls-Royce also tested a full engine on hydrogen on the ground recently. So there is progress on that front. The second way is to use it on an electric aircraft. So you use the chemical properties of hydrogen, you combine it with oxygen in a device called a fuel cell that acts very much like a battery. So it produces electrical energy, and then you can power an electric aircraft, but instead of having a battery, you have a hydrogen fuel cell. And below, it's a photograph I took at the museum in Stuttgart. It's the Mercedes-Benz Museum. And you can see a fuel cell on the left, and then an electric motor. And this particular application is for a car. But once you have the fuel cell and the electric motor, you can connect anything you want to the other end. It can be a propeller, it can be a wheel of a vehicle, it can be anything else. So what are we doing in IATA about hydrogen aircraft, and what are the focus that we have at the moment? So a lot of the focus that we're putting now is how does this aircraft operate at an aerodrome, and how are the procedures going to be different. So on the top left, you see an aircraft with some circles around. Those circles represent fueling safety zones. So at the moment with kerosene aircraft, the fueling safety zone is 3 meters. So from the point you plug the hose underneath the wing, there has to be a clearance distance of 3 meters. So we're exploring now how much this is going to be with hydrogen. If it's 3 meters, it's fine, no problem. If it's 20 meters, like the red circle, then that might have some issues. Why? Because it means that while you are refueling the aircraft, you might not be able to cater the aircraft. You might not be able to remove the water from the lavatories. You might not be able to board it. So this means that activities won't be able to get parallelized, and they will have to happen in series. And this extends the turnaround time of the aircraft, and this means less utilization of the aircraft for the airline. So the graph on the bottom right shows different turnaround times, and this is again from Flight Zero. NSA is no simultaneous activity. So what would happen if you have to do refueling completely separate? Your turnaround time goes much higher than the average, which is the gray line. If some simultaneous activity is allowed, then the turnaround time decreases, and if there is simultaneous activity, as it is with jet fuel, then you can turn around that aircraft in the same time as you would a normal jet fuel. So this is an aspect that's quite important for airlines. Another one on the bottom left is the personal protective equipment. Hydrogen will have to be stored very, very cold, minus 250 something degrees. So will the operators need to be protected for cold temperatures? Will they not? These are all data gaps. We don't know. On the top right, and I'm sorry I'm moving people a little bit around the screen, but hydrogen is much lighter than jet fuel, which is very good. We will carry less fuel on board, but it occupies a larger volume. This means that for refueling the aircraft, we may take more time if the hose is the same diameter. So we might need a hose of larger diameter to be able to pass more volume in smaller time. And that hose will have to be insulated because the hydrogen will be cold. So we're also wondering, do we need to have a robotic arm that will help and assist the hose on refueling? Is the refueling process going to be the same, etc.? So a lot of our attention is focused on this area of how will this aircraft operate at an aerodrome, and what are the different characteristics, and will the operations for an airline change? So I'm just putting open questions. We don't have answers to a lot of these questions, but just showing you a little bit of flavor of what we're looking. Now I will focus on the airport very quickly. So how we see the development of hydrogen use at airports. It already started. We already have forklifts powered by hydrogen. This is a photograph of Kansai Airport, a Toyota hydrogen forklift. We also have buses that are bringing passengers to airports, or even operating within the airport environment. So I visited Toulouse Airport, and they had a hydrogen-powered bus that took passengers from the terminal building to the aircraft, and they are producing the hydrogen on site. So we already see this sort of creeping in onto the airport environment. There are examples, of course, as well in Australia, in Christchurch Airport, of people thinking about this and already looking at implementing it. Then we have smaller aircraft, perhaps retrofitted aircraft, like what ZeroAvia is doing. And then post 2035, the larger aircraft, like what Airbus is developing with the ZeroE. The things that we are looking at around the airport is, how do we bring hydrogen to the airport? So we are looking at 3 scenarios. So one is hydrogen can be manufactured off-site, completely off-site, and then brought to the airport by trucks. This happens at many airports, so it's not uncommon, and some airports receive their fuel entirely by trucks today, their jet fuel. So could we replicate the same for hydrogen? And this minimizes the infrastructure at the airport at the beginning, perhaps simplifies things. In our assessments, one truck can cater for about 4 small regional aircraft, or about 1 to 2 narrow-body aircraft. So that gives you an idea of the dimension. And in that case, the airport would need a tank, and then the trucks to come and dump the fuel onto that tank, and some infrastructure to distribute the hydrogen around the airport. Scenario 2 is hydrogen gets manufactured offsite and then transferred via a gaseous pipeline to the airport, and then it gets liquefied at the airport and then stored. So this is more applicable to larger quantities. Building pipelines is very expensive. I've seen different orders of magnitude, but about $1 million per kilometer is a sort of good rule of thumb. Can be less, can be a bit more, but it gives you an idea of the investment. So this is only justified when you have larger planes, a larger aircraft, and larger airports where the hydrogen is needed. And then scenario 3 is a scenario where the hydrogen is manufactured on site. So you don't bring hydrogen atoms, you bring electrons to the airport, and then you make the hydrogen on site. What we have seen is that this is difficult to scale up to many sort of hundreds of operations of aircraft. It's already happening today. As I said, Toulouse Airport is an example, but at a small scale. But very soon you seem to be running out of capacity, space, power. It might work for some airports that have a lot of land, but it might be challenging for some others. So this is very case by case dependent. So one of the works that we are leading in IATA, along with the manufacturers, ICCAIA is an organization of aircraft and engine manufacturers, and with the airports, or Airport Council International, is a task force where we are developing a concept of operations of hydrogen aircraft, and we're covering a lot of the things I've mentioned. So we're looking at mainly the operations around the aerodrome, so approach, landing, taxi. You can see there the planning, refueling, catering, de-icing, etc. And we're wondering ourselves, how is this going to be different to a kerosene aircraft? How is it going to be similar? What will change? What won't change? And then we're trying to review how this is going to change international standards or recommendations. So, for example, the aerodrome design and operations manual from ICAO already has recommendations on how an aerodrome has to be designed. Will this need to be modified for hydrogen? What will change, etc.? So we're looking at things like clearing distances, refueling times, firefighting and rescue, maintenance, etc. So this is a document we are developing, and we do plan to make that public once we finish. Now, I'm just want to show you some of the initiatives that we know of. And you can see there are a few in Australia, also New Zealand, in different parts of the world. So it's really, really spread out. 35 airlines and 44 airports that have publicly announced projects on hydrogen, either investing on hydrogen aircraft themselves or doing a feasibility study. And this is about, the numbers have more or less tripled in the past 2 years. So this chart is always out of date. The first time I showed it, it was about 10 airlines and about 12 airports, and that was 2 years ago. So you can see the progress. So what is happening in other sectors? This is a lot of those photos. I took them myself, so I can assure you these things do exist. So hydrogen taxis in Paris and hydrogen cars, hydrogen buses in London and in Toulouse, a hydrogen excavator that I saw in Glasgow. The ones on the right I haven't seen myself, but trains, stations, cars, etc. So we see other sectors also moving ahead. And why am I showing that slide is because there are a lot of things that we can learn from this sector. So they figured out how to refuel these vehicles, how to transport the hydrogen safely, how to fill a vehicle with passengers and transport it on the road with a lot of cars around them in a transportation mode that has a much higher accident and incident rate than aviation, and they do this safely. So what can we learn from those sectors in terms of safety, procedures, materials, refueling standards? There's a lot to learn, and we are keeping a close eye on what is happening. The other reason why I show that slide is to show you how the hydrogen landscape will look and looks today. So today the global economy uses about 100 million tons of hydrogen, mainly for oil refining and for ammonia for fertilizers. And you can see that's the chart there on the left. It's from IRENA. If the global economy transitions aligned with 1.5 degrees, etc., there will be about 650 million tons of hydrogen, so quite a lot more. Now, this is good news for us because there's going to be more of it, the price will come down, the availability will be higher. So this is going to happen without us doing anything. So the availability of this energy carrier will be there for us. However, in our roadmaps, we have predicted that about 100 million tons of hydrogen will be needed in 2050. So about a quantity equivalent to the hydrogen used today. Most of it is actually for making SAF, and about 14 million tons for hydrogen aircraft. So this is going to be a challenge, even though there will be maybe, hopefully, 650 million tons of hydrogen in 2050. We will still need a lot of that. So this is an important message. Aviation needs hydrogen, needs clean hydrogen, and we need to keep advocating for that. The other part of this coin is that we cannot do this alone. So we really need the whole planet to move towards decarbonization. And Rachel will also speak about what happens when we don't do that and how we now need to adapt to a warming atmosphere. So it's in our own interest to decarbonize, as one might say. So we depend on the planet to do that, because if this doesn't happen, if we don't move to cleaner energies, if we don't move to clean hydrogen, then it's going to be very difficult for aviation to do it on its own. And with that, I will stop the talk. I know it was a bit rushed, but I hope I could stay within the 20 minutes. And I'm happy to take any questions if there's time, and if not, I can answer them on the chat. Thank you, Susanna.
Brilliant.
Thank you, Tim.
Thank you very much, Alejandro. Very interesting, very much to time. That was great. On the hydrogen ecosystem and some kind of insights into what we can expect to see in the future. Now, as Suzanne mentioned, we are conscious that Alejandro's got to rush off. It's very early, late night, I should say, where he is in Montreal. There is a detailed question in the chat on nitrogen oxide. What I would do is ask you a general question now, and then when we go on to Keith, if you could then type in and do that one, there may be some more detailed one, and then it's up to you how long you feel awake to stay up. So I think my just oral question is, you mentioned milestones, you mentioned the time frame, but you also mentioned different scenarios, some more aggressive than others. And you had 130 milestones. What, in shorthand, do we need to do to really accelerate the uptake in hydrogen or shift? Or is there anything that can accelerate this?
Yeah, I guess the list is very long, Tim. So I could speak another 20 minutes. But first of all, I think more investment into de-risking the key technologies, some of them which are on the roadmap. So investment from governments, investment from private companies to mature and de-risk things like fuel cells, hydrogen tanks, heat exchange systems, hydrogen combustion units. Also certification, that's a big bottleneck. So one of the asks here is, for the certifying authorities, if something comes on their way for green technologies, I call them, but hydrogen or battery electric, etc. Well, it would be really nice if they get prioritized, so that they can sort of fast track. So for the certifying authorities, it would be a good idea to set a sort of fast track so that these technologies can progress faster. The certification, of course, has to be super thorough. It's going to take some time, but it shouldn't be stuck on paperwork. So that's one of the messages. And of course, scaling up green hydrogen. So the worst thing that can happen is that we develop an aircraft and then there's no hydrogen to refuel it. So this hydrogen is going to be used for other sectors. So hopefully, a solid strategy on green hydrogen scaling up for aviation and other sectors.
Yeah, I've just seen two more quickly come in the chat, which are great. I think I'll ask you one, and then the others, if you've got a chance to type in them. And it's the general one from Robert. It says, is enough being invested in hydrogen aircraft tech? Now, the obvious answer is no. But can you just say a bit about investment and how you could see it might grow, or in which parts of the tech it's really needed?
Yes, thank you. So what we have tracked is, we've been tracking announcements for investment for current and future, and funding programs and feasibility studies and so on. If we agglomerate the investment in technology and airport feasibility studies and everything that we have access to, it's about $4 billion. So it's quite considerable. but it's definitely not enough to be able to bring this aircraft into service. So one aircraft program, you know, when an OEM, big OEM wants to do an aircraft program from beginning to end, is about, you know, 10, 15, 20 billion dollars, right? So that's the order of magnitude, 10, 20, 30 billion dollars. So that's the amount of money to bring the aircraft to maturity. But then, of course, there's investment for the airport infrastructure, for the hydrogen downstream, for all of these things. So that has to be accelerated, and it has to be very strategic as well. In, as I said, de-risking some of the key technologies. I mean, the aircraft will still use the same materials, you know, wings, fuselage, everything, but there are some key things that have to be de-risked and matured.
Yeah, brilliant. No, thanks very much, Alejandro. I really appreciate your time. There are a few more coming in the Q&A. If you, as much time as you have, feel free to respond, and the rest of the panel can touch on them. So thank you very much. Really appreciate it. So we're now going to move on to the second speaker, joining us from the UK, early morning with him. Please welcome Professor Keith Shine. Thank you for being with us. So a quick biography. Keith Shine is Regius Professor of Meteorology and Climate Science at the University of Reading, UK. His past work has included a focus on non-CO2 aviation impacts, including the impact of contrails, NOx, and water vapour emissions. He was co-author of a recent critical review of uncertainties mitigating such non-CO2 climate impacts from hydrocarbon fuels. That paper was published in Environmental Science Atmosphere Journal. Keith will present about non-CO2 impacts of aviation. Thank you very much, Keith. The floor is yours. Go for it. Thank you.
Thank you very much, Tim. So good morning, or good whatever, everybody. So yes, I'm very much presenting my personal view here, but of course my knowledge base has been built up by a lot of interactions with a lot of people over the years. So that I'm going to pose a few key questions. Can contrails be avoided? And the answer is yes, very clearly. It was an issue for the military 70, 80 years ago, and they solved that by flying at different altitudes. But most importantly, from our perspective, can they be avoided now in a way that the potential climate benefit can be reliably quantified? And I believe the answer is no. And in a way that we can guarantee that perverse outcomes, as in causing even more climate change, can be avoided. And I believe the answer to be no. And might it be possible in the future? Well, yes, definitely. As I'm going to explain, my belief is we can demonstrate that it can work in a perfect model environment where we know absolutely everything, but in the real world, we're some way off that. So this is a really active research area. I've just shown the front page of several papers that have come out rather recently, and I can't even claim to be keeping up with all of those, but it is an active research area. Progress is being made, and there's quite a few differences of opinion out there. So these are the things I'm going to go through, talk about predicting contrail occurrence, knowing the properties of the contrails well enough to look at their impact on the radiation or energy budget of the planet, and then move on to the climate impact, and then finally talk a little bit about how we compare CO2 and non-CO2 climate impact. So let's start with the first area. So just some contrail basics for those who are unfamiliar. So if you live in a cold environment, then the physics of contrail formation is just like seeing your breath on a cold day. So unsaturated parcels of air coming out your lungs and outside mix together, saturate, and you get a transient cloud form. Now that cloud normally dissipates very quickly as the contrail, your breath, mixes with the surrounding air. But in the upper troposphere, so we're talking 10 kilometers or so up in altitude, an unusual situation can occur where the air is so-called supersaturated with respect to ice. So these are ice supersaturated regions, which means they want to form clouds, but there aren't the nuclei in the atmosphere for the water to condense. And once a contrail forms, that supersaturated air says, "Hey, great! I've got some particles that I can condense on." So the supersaturated air condenses onto the frozen droplets, causing persistent contrails, and these can spread out to what are nowadays called contrail cirrus. So the three stages on a short time period, you see a linear contrail behind the aircraft, and we can predict those quite robustly, but often they dissipate very quickly. If the air is ice supersaturated, then the contrail persists for tens of minutes, and then it can last for even longer as it spreads out to form these contrail cirrus. And what I have to stress is that not everywhere has these ice supersaturated regions. This is a rather old plot, but uses satellite data to locate areas. So areas in yellow regions where these ice supersaturated regions are quite common. So we can see over Europe, North Atlantic, they're quite common. Over Australia, they're rather uncommon. And of course, where contrails occur is a combination of this, or persistent contrails, I should say, is a mixture of this plot with where the air traffic is. So here in Reading, we've got lots of aircraft flying over us, and the ice supersaturated regions are quite common. So I see contrails probably most days. But one thing I haven't got time to go into is that these ice supersaturated regions aren't static things. They're very dynamic. They're patchy in time. They're patchy in the vertical and the horizontal, and they're determined by the prevailing weather conditions. And this is really the root to one of the problems. If they were static and always there, it would be a much easier situation. So here's just a picture from my back garden. It's dark out there now, but showing a day that's not that uncommon. We've got persistent contrails, line-shaped features, but we can also see these older contrails spreading out into contrail cirrus. This highlighted region here is showing that on the same day, we've got some non-persistent contrails. This contrail is dissipating very quickly. So it could be due to the engine in the aircraft, but my suspicion is that it's flying a little bit higher than these other aircraft. And if it flew a bit lower, it would be back in the ISSR, to coin a phrase. So just one example of the difficulties. There was a very important trial looking at possibilities for contrail avoidance. So it's a Maastricht 2021 trial. So this was a pioneering study by Sausen, where they made real-time decisions on whether they were going to reroute aircraft. So this is very much my interpretation of their results. So we have here a contingency table, which says on days whether persistent contrails were predicted, yes or no, and whether persistent contrails were observed, yes or no. And we can see if we look at the predicted versus the observed, then more often than not, when a contrail was predicted, a contrail wasn't observed. So that indicates a failure, if you like. And if we just take the cases where persistent contrails were either predicted or observed, so if we add up these three cases, then the forecast was correct only 36% of the time. And if we look in the literature, other that have looked at the possibility of predicting these ice supersaturated regions, these papers by Klaus Gehrens and his colleagues, you can see statements here that say the present state of the science is very difficult indeed to predict these ISSRs. So that's predicting the contrail, but of course that's only one part of the process. Not only do we need to predict them, we need to calculate how much they're perturbing the energy budget and then how they're affecting climate. So this is a classic diagram from a wonderful paper by David Lee and many colleagues, which characterize the radiative forcing from aircraft. So the red bars is when it's a positive radiative forcing tending to warm climate. The blue is when it's tending to cool climate. And on the top here, we have the contrail cirrus radiative forcing, and in the bar below, we've got the CO2 radiative forcing. And one thing just to stress from this paper is that the uncertainty in the contrail radiative forcing is huge. It could, just from their expert assessment, it could range from anywhere from about half the CO2 forcing to more than 3 times the forcing. And one thing I don't have time to talk about, there's also an issue with these so-called aerosol cloud interactions, which is so uncertain that Lee et al. Weren't even able to put a best estimate on it. And some of this forcing might originate from the processing of soot particles within the contrail. So this is related to the contrail forcing. And the size and even the sign of this forcing is poorly constrained. I won't labour it, but there's many other non-CO2 aviation forcings that depend where and when the emissions occur. So one of the punchlines from this paper is that the aviation CO2 radiative forcing is about 1.5% of the total CO2 from human activities. But when we factor in the non-CO2 effects, it could range from 1.3 to 14%, but that's neglecting this very uncertain aerosol cloud forcing. The other thing that has to be made clear is that the actual radiative forcing, the actual drive of climate change from contrails, is the residual of 2 opposing terms. So contrails reflect the sun's radiation, which is cooling the planet, but they also trap infrared radiation, which is warming the planet. And this shows a very nice paper which showed the evolution of a contrail cirrus outbreak over many hours over the North Atlantic. And we've got two things here, the long wave forcing, which is always positive, and the short wave cooling, which is depends on a lot of things. For example, the how high the sun is in the sky. And we can see that the net effect actually varies from warming to cooling. And so again, to characterize what is going on, we have to track a contrail over its whole, or a contrail cirrus over its whole lifetime. Now, radiative forcing is used a lot in this area to characterize climate impacts. And radiative forcing has a lot of different flavors nowadays. Radiative forcing is the perturbation in the top of the atmosphere energy budget. And most contrail climate studies calculate this radiative forcing. But these days, the Intergovernmental Panel on Climate Change prefers a refined definition called ERF, effective radiative forcing, which allows some extra adjustments in the atmosphere to occur. And the problem is that there's very few studies in the literature of this ERF for contrails. But what they show is that the ERF is systematically lower, sort of typically a half or less than the radiative forcing. So on the Lee et al. Study, there's 2 columns of radiative forcing, but what we believe to be the ERF, but what we believe to be the more refined measure, the ERF, is around half of the RF. But there's sparse literature on this. And the basic reason why this decrease occurs is that contrails occur at the expense of natural cirrus clouds. So if we're decreasing the amount of natural cirrus clouds, it means effectively the contrails are having less of an impact than we think they are. And this understanding of the contrail RF is evolving. And so if we look at studies since the Lee et al. Study, there's many studies have come out, for example, even exploiting satellite observations during COVID. And we can see their best estimate was around 110, but many of these recent studies are coming in lower than that. And there's been actually rather few studies of the ERF since this study, and they're coming in at around the same level as this one, but they're also noting many uncertainties. So one of the issues that sometimes also is not recognized is that the radiative forcing isn't the climate impact of the contrails. We have to go one step further. So in the previous bars, I talked about the RF and the effective radiative forcing. But what we most care about is, of course, the surface climate. It could be precipitation, etc., but let's just focus on temperature. And the temperature is related to the radiative forcing in an approximate way by this simple equation. Lambda is climate sensitivity, which is a chronic uncertainty in climate science. But it also turns out that the value of lambda depends on the nature of the radiative forcing. So it could be different for CO2 than it is for contrails. And there's in fact, to my knowledge, only one calculation using a sophisticated climate model that has done that. So what they say, this is more relevant than radiative forcing, and the one study that's available from DLR in Germany indicates that the efficacy of contrails at causing climate change is much less than the efficacy of CO2, so less than half. So it's reduced from here, going from here to here it's reduced, and going from here to here it's reduced further. And this is a little cartoon to show the effect using radiative forcing. The contrails dominate over CO2, including the effective radiative forcing reduces the gap, and then going to surface temperature, it actually changes the order of these forcings. But I emphasize this is based on one system model, and other system models may show quite different results. So we have to be very cautious. So finally, hoping I'm on time, we'll come to the issue of comparing CO2 and non-CO2. I can't do this subject great justice in the time available. But just to understand that if we do divert aircraft to avoid contrails, we're likely to emit more CO2. And a successful reroute, this is a little cartoon we put together. This is the original route. It might be the minimal fuel route, which caused contrails, and we divert. We cause extra CO2, but we avoid a contrail. And that's a successful reroute as long as the amount of CO2 emitted doesn't overwhelm the effect of the avoided contrail. But there's other scenarios which are less favorable. One of them is where we divert to avoid a contrail, but the predicted contrail didn't occur on the other flight, so we've emitted extra CO2 for no gain because we haven't avoided a contrail. Or another scenario here is where contrails occur on both routes, so we've diverted but caused a contrail anyway. And of course, a worst case would be where you divert, cause a contrail as well as extra CO2, but the original route didn't have a contrail as predicted. So there's lots of possible outcomes that are not favorable. And one of the things I think is not really properly and widely understood is one of the difficulties is that CO2 has a very long persistence time in the climate system. This is a very nice diagram from the IPCC fifth assessment report. This imagines emitting a pulse of CO2 at time zero, so a single flight, for example, and the CO2 in the atmosphere is very persistent even after 100 years. Around 40% of that CO2 remains. Now that's very different to the case with contrails, where they, even a long-lived contrail, we're talking maybe a day, so it disappears very quickly. So there's a real problem in comparing the climate impact of a CO2 emission contrail formation because of these vastly different timescales. And this is just one example. There's many possible ways of coming up with a metric to compare CO2 and contrails. And this diagram from a recent paper by Barella et al., which I was slightly involved in, this showed the orange bar is the radiative forcing or the CO2 equivalent due to contrails. The CO2 bar is always 1. And depending on what metric you choose and what timescale you can use, using a very short timescale, it looks like the contrails are much more important than CO2. But as you go to longer timescales, then the relative importance changes. As you go to different metrics, going away from the GWP to other metrics, then sometimes the effect of the contrails can look even smaller. So I don't have any magic answers for this, but one of the important things I believe in climate policy is that the metric that is used should match the aim of the policy that's being implemented. So just to conclude then, issues that need addressing, we have to reliably forecast the occurrence of these ice supersaturated regions. One thing I haven't touched on, but so we also have to forecast the degree of ice supersaturation, whether the air is heavily supersaturated or lightly supersaturated, course that determines the thickness of the contrails and their properties in terms of reflecting and absorbing solar and infrared energy. We have to know the size of the radiative forcing. So even if we knew these very well, that's not necessarily translate to knowing the radiative forcing with sufficient confidence. And if you're going to avoid contrails, you have to be able to calculate the radiative forcing of the contrail you've avoided, which is a little bit mind-bending, and you have to know that with sufficient confidence. You also have to verify the climate impact of the contrail over its entire lifetime. And again, this verification, I think, is a serious issue in this area. And then we also have to build a consensus on how we're going to compare the climate effect of CO2 emissions with those of the avoided contrail. And my view is that the technology readiness level in this area is about TRL equals 2, which means that it's in its exploratory phase. So we can demonstrate it in a perfect model environment, but we were well short of doing so in the real world. So thank you very much for listening. That's me.
Thank you, Keith. Absolutely fascinating, and thanks for finishing on such a punchy note, actually, with the technology readiness level. And it just highlights to me even more so that, I mean, the underpinning science around contrails is absolutely essential. So thank you for sharing and explaining it to the audience so well. So I'm looking forward to some of the questions that people no doubt will post in the Q&A for our discussion later. Our third speaker today is joining us also from Europe. So thank you to Rachel also for getting up early. Rachel Burbidge is from Eurocontrol, and she focuses on climate change adaptation and resilience, has been doing that since 2009, and offered the organization's groundbreaking challenges of graph work on climate adaptation, including also several journal articles. Rachel co-chairs the European Aviation Climate Change Adaptation Working Group with ACI Europe, and she also co-leads the climate adaptation resilience work for ICAO, for the CAP, Committee on Aviation and Environmental Protection for Airport and Operations Working Group. So today we will learn a little bit more about the climate risks for airports. And I'm handing over to you, Rachel. The floor is yours.
Great. Thank you, Suzanne. Thank you very much for the introduction and for the invitation opportunity to be here today. Good morning, good afternoon, and good evening to everybody. So I'm going to talk about a slightly different aspect of aviation and climate change, as we've had two really great presentations from Keith and Alejandro, really insightful. Thank you. And I've enjoyed them very much. And I'm just going to, hold on, right. Okay, there we go. So just before I start the main presentation, I'm just going to say a couple of words about the organization I work for, because I realize that probably not everybody who's on the webinar today will know who we are. We are the European Organization for Air Navigation, but we are an intergovernmental organization. We have 41 member states, and our main role is to support those member states in the safe and efficient management of the European airspace. But we also have other diverse roles, such as collecting the route charges from airlines for using that airspace, research, training, innovation, and environment and sustainability, which is where I fit into it. So what am I going to talk about? Well, we know that as a sector, we need to rapidly reduce our emissions and decarbonize. And we've had two excellent presentations talking about various ways that should or maybe shouldn't be done from Alejandro and Keith. But I'm going to flip things around a little bit and look at the opposite side of the story. And that's, what will climate change's impact be for the aviation sector? So unfortunately, however quickly we as a sector or society in general decarbonizes, we are still locked into some amount of climate change because of historical emissions. So we need to understand how climate change will impact the aviation sector and to take action to adapt and build resilience to those impacts. So I think aviation is used to dealing with disruptive weather, but in recent years, we've had some extreme catastrophic events which have impacted the sector around the world. We've had catastrophic hurricanes in the Caribbean. In Japan, Kansai Airport was inundated by a typhoon and a storm surge and closed for over 2 weeks. More recently in Brazil, a prolonged period of extreme rainfall inundated Porto Alegre Airport. It's been closed for almost 3 months, and I believe will finally start to reopen with a short number of flights tomorrow. So quite an extreme impact. And then just last week in the United States, there was a catastrophic Hurricane Milton, well, there were many catastrophic impacts from that hurricane. But for the aviation sector, there was a big impact in terms of cancellation of flights and delays. And this also had a knock-on effect around the world in terms of cancellations and delays, for example, because of aircraft not being where they were expected to be. So I think we can't yet attribute any individual event to climate change with absolute certainty, but there are an increasing number of attribution studies that can demonstrate that climate change is already making weather events more extreme. I think there have been studies that show that the extreme rainfall in Brazil that inundated Porto Alegre Airport was made more extreme because of climate change. And in the UK in 2022, there were temperatures of 40 degrees centigrade for the first time ever. And it was demonstrated that this would have been practically impossible without climate change. So these are the sort of events that as a sector we need to start to prepare for and to adapt to. And there is another challenge in that traffic is growing and is projected to increase. According to the Airports Council International, we're projected to see almost a doubling of global passenger traffic by around 2050. There will be regional differences, but in general, traffic is going to grow. And this is a challenge for 2 reasons. Because if an airport or an airspace sector is operating at or close to capacity, and there is a disruption, then the impact of that disruption is greater and the recovery time is longer. So these are really 2 challenges that I think we need to look at together. So I'm just going to take another couple of minutes now to talk through some of the impacts of climate change for the aviation sector. I think storms are already an impact. I mean, we have major storms such as hurricanes, typhoons, obviously have a severe impact. But even a regular storm can have a fairly significant impact in terms of delays or cancellations and diversions. Storms can damage infrastructure. The extreme rainfall that often accompanies a storm can flood infrastructure. And because of climate change, we are expecting an increase in lightning strikes, which has an operational and safety risk. So at Eurocontrol, we wanted to understand a little bit more what this might mean for future air traffic operations. So we carried out a study in conjunction with the UK Met Office and Aegis Aviation on climate change risks for European aviation. And we looked at how the impact of storms might evolve out to 2050. And we found that actually the occurrence of storms might decrease slightly, particularly in the south of Europe, but that when there is a major storm, because it would be stronger, it would be more intense, then the impact will be greater and the delay associated with that storm might increase. So this is a study just for one region, but I think even though things will vary from region to region, it gives us an indication of the kind of impacts that we need to be trying to understand and we need to be trying to prepare for. Higher average and extreme temperatures are already being experienced in many locations around the world. They can have impacts for aircraft performance. They can cause damage to airport surfaces and infrastructure, to IT equipment. And for people, for passengers and personnel, they can have some health effects in the term of heat stress. I think sea level rise in most locations of the world is probably a longer term impact, not everywhere, but this could lead to permanent inundation of airport infrastructure, in extreme cases, relocation of airports. Storm surges we are seeing right here, right now. We've seen with the hurricanes in the Caribbean, in the US, in the last couple of weeks, that we can have quite extreme storm surge. And of course, this has operational impacts, infrastructure impacts. There is a study by Yusudian and Dawson, which looks at the impact of sea level rise for airports around the globe. And they find that for sea level rise, it's equivalent to 2 degrees centigrade of global warming. Around 100 airports will be below mean sea level, and over 360 will be in the coastal floodplain. And many of these are important hub airports that serve millions of passengers a year. So the impact on global connectivity could be severe. I think as well as focusing on major hub airports, we also need to think in terms of sea level rise and in general about smaller airports. There are many, many thousands of small regional local airports in the globe that are really important for local communities, connectivity, regional economies. And so the focus should not just be on the major hub airports. We also need to think about those airports as well when we're adapting to climate change. If you have operational impacts at an airport, that does equate to a cost. So as part of our European climate change risk study, we did look at the potential costs of airport closures. And what we found that was for a one-day closure of a large airport, so that's an airport with over 100,000 movements per annum, we were looking at an average cost of around 18 million euros per day. Now, that is an average that will vary greatly from airport to airport and from region to region, but I think that gives us an indication of the sort of costs that we might be looking at. Wind patterns can affect aviation in various different ways. At ground level, if you have a deviation from the prevailing wind direction, this can have an operational impact. En route, this can, if you have changes to high altitude winds, for example, this can affect flight times and routings. And the aircraft on the left there is a Norwegian Air aircraft, which in January 2018 crossed the Atlantic in a record-breaking time of 5.5 hours. It was so quick that the crew didn't actually have time to serve breakfast. That was since surpassed in 2020 by British Airways aircraft, which crossed in around 4 hours 30. So they are quite extreme examples, but I think they give us an indication of how high altitude winds might evolve. So as an air traffic organisation, we wanted to understand a little bit how this might evolve out into the future. So we did a study which looked at 3 route groupings, which you can see on the left of the slide there. And for each route, we looked in both directions and for winter and for summer. And we found that for all 3 routes in both directions and in both seasons, with the exception of Northern Europe to the Canary Islands in the winter, by 2050, we were seeing a average shortening in flight time of around 1 to 5 minutes per flight. So on a flight by flight basis, that isn't particularly significant, but again, it is an average and it does give us an indication of the sort of impacts we might start to see in the future. In terms of turbulence, unfortunately, recently we have had some quite severe, sometimes tragic incidents of turbulence encounters with aircraft. And equally, unfortunately, scientific studies do demonstrate that because of climate change, incidences of clear air turbulence are projected to increase. This doesn't necessarily mean that we will have more turbulence encounters, because turbulence forecasting tools and models are improving. But I think it does demonstrate that we do need to keep putting effort into improving those models and those tools to try and avoid as many turbulence encounters as possible. The other potential change that we might see, I think, is a change in tourism preferences, which in turn could lead to a change in traffic demand. In Europe, in the last couple of years, we've had some quite extreme summers. We've had some really extreme temperatures in the south of Europe and big challenges with wildfires. And there's a lot of anecdotal talk about tourists maybe starting to change their preferences a little and to start to take their summer vacations in cooler locations in the north of Europe rather than traditional summer holiday destinations in the south. So we did take this as part of our climate change study, and we used something called the Tourism Comfort Index, which is an indication of how suitable the climatic conditions in a particular location are for tourism. On the left-hand side there, you have the present day, and then the middle column is projections out to 2050. And you can see in that middle column that for the summer, June, July and August, and the autumn, September, October, November, for really a large part of the European region, you're starting to see conditions that are increasingly favourable for tourism. And in fact, we were even starting to see changes already by around 2030. So we don't think this will have a major impact in the short to medium term, but we think we might start to see a slight northwesterly shift in tourism patterns. We don't think tourists will completely avoid or abandon traditional summer holiday destinations, but you might see some starting to move slightly towards the more northern regions instead. And we might also, for travellers that are able to travel outside of the traditional summer period, see a sort of broadening of the vacation period into the spring and the autumn months. So we don't think this is going to happen overnight, but it is something we need to start to think about. So I think we're starting to have a reasonable understanding of knowledge of the effects and impacts that as a sector we might have to prepare for. What we need to start really doing is ramping up our efforts to adapt and build resilience to those impacts. I think good practice is generally seen as carrying out a climate change risk assessment and then developing a climate change adaptation plan. So it is really important for individual organisations to carry out their own climate change risk assessment to understand the specific risks that they might be vulnerable to, because this will be highly dependent on their geographical location, their type of organisation and operations, the base climate, how the climate is projected to change. And then following that, they can start to look at identifying adaptation measures, which again will be highly dependent on the specific organisation. And I think we are seeing more organisations, particularly airports, I think, that are starting to take action. But we do need to do more, and we do need to work more collaboratively as a sector. We are a highly connected network. We've seen from, for example, Hurricane Milton last week, that if you have a disruption in one part of the network, this can have a knock-on effect across the system. So we do need to make sure that we are working together to build the resilience that we need. So in Europe, we are trying to do this through the European Aviation Climate Change Adaptation Working Group. So this is a group, I think we're currently around 39 organisations, mainly airports, also air navigation service providers, industry organisations. And our main objective is to provide peer-to-peer support, develop good practices and guidance to support each other in climate change risk assessment and adaptation planning. But I think this is definitely an initiative that can be expanded both within the region and perhaps wider than that. I also think there is a really important role for the research community and for the aviation sector to work together. A few suggestions on the slide there. I'm not going to talk through them all, but there's two that I'd like to highlight that I think are probably most relevant to this discussion today. And that's the geographical coverage of research in the field and also the uncertainties. So there is an increasing amount of research in the field in regions such as North America, Asia Pacific, Europe, but there are some regions of the world such as Africa, South America, where there is a real significant lack of research on how climate change might affect aviation and the measures that we need to take to build resilience to that. There have been a couple of really good recent studies. Very recently, Holmes et al. Produced a paper that does a real deep dive into the impacts of climate change for the Australasian aviation sector. And we worked with the Airports Council Latin America and Caribbean to do a study on the impacts of climate change for that region. But there is still a real research gap here that I think us as a sector, we need to work with the research community to cover. And the other big challenge is the uncertainties. We know we need to adapt. We know we need to build resilience, but how much do we need to adapt and how quickly do we need to do that? And I think it's not simple, but it's relatively simple to prepare for high probability, low impact events, such as a slightly stronger than average storm. We know what we need to do for that. But it's much harder, much more challenging to prepare for the low probability, high impact events that we perhaps don't really understand yet, such as a 1 in 1,000 flooding event. And we had an example of this very recently in April this year at Dubai International Airport, where they had something like the equivalent of 2 years of rainfall in 2 days. And perhaps, admittedly, 2 years of rainfall in the Middle East is not as much as 2 years of rainfall would be in other regions. But if you're not accustomed to that and you suddenly receive that quantity of precipitation at one time, then drainage systems are not sufficient, overflow systems don't work, and this is when you have major flooding impacts. So I think this is where we can perhaps work with the research community to understand to what extent do we need to prepare for this category of event, and there's probably a very important role for the insurance industry here as well. So I'm going to finish up. I think hopefully I'm still just about in time with a couple of words on the role of policy. So we are seeing an increasing number of policies nationally, regionally, globally to try and drive decarbonisation in the aviation sector. At global level, we have the CORSIA, the ICAO Carbon Offsetting Scheme for International Aviation, which intends to drive emissions reduction at global level. In terms of driving uptake of sustainable aviation fuel, SAF, we have two very different approaches on either side of the Atlantic. In the United States, we have a very market-driven approach where large amounts of funding are being made available through the Inflation Reduction Act to drive development and implementation of sustainable fuel. Whereas in the European Union, a much more regulatory approach is being taken, and here a mandate is being introduced, which will increasingly increase the amount of sustainable aviation fuel that needs to be made available at airports to airlines. It starts very small, something like 2% per annum, but grows quite significantly over the lifetime of the policy. Which is more effective? I think that remains to be seen. Possibly some combination of the two would be the most effective, but we will find out. But it does raise the question of whether it's time for more policy initiatives to drive adaptation in the aviation sector. And at present, at least to my knowledge, there are relatively few policies driving or covering adaptation at a national level for aviation sectors, and nothing really at regional or global level. But what we have seen is in the United Kingdom, the 2008 Climate Change Act mandated the 10 largest or busiest, most strategic airports, the Air Navigation Service Provider and the Civil Aviation Authority to produce adaptation reports. They've been producing those since around 2010, 2011, and they are now in their 4th round of reporting. So they have really quite mature, well-developed adaptation plans and programs of adaptation measures. When we did the study for ACI Latin America and Caribbean, we carried out a survey as part of that work where we asked airports to what extent they were engaged in risk assessment and adaptation planning. We had 35 responses, which covered 53 airports. And from those responses, the one airport that had implemented an adaptation plan had been mandated to do so by their government. So I think that is the million-dollar question. Is it time for more mandates, probably at national level, for airports and aviation organisations to carry out climate change risk assessments, implement adaptation plans? I can think of good reasons why it is. I can think of good reasons why it isn't. So I think I'm going to leave it there, and maybe we can get into that in the discussion. So with that, thank you very much, and I will hand back to Tim and Suzanne.
Brilliant. Thank you very much, Rachel. Very insightful, very relevant and topical to a lot of that. Thank you for posting questions to the speakers. I can see at the moment there's 5 in there. Carry on doing that. We'll try and answer some of them today. We might feed some forward to next week as well. So I'd like to ask the speakers to join us now for the Q&A. So Alejandro naturally has had to leave, but I'd like to kind of have Keith and Rachel joining me on this virtual stage. And let's start with the first question. So over to you, Suzanne.
Yeah, maybe I'd just pick one that was just posted by a participant. It's a very open one, so you can share whatever you feel excites you. But the question is basically, what would you see as the most critical action or outcome or policy that you want to see activated, to accelerate decarbonization and climate risk management in the aviation sector? Either of you, Keith, would you like to make a start? What would you see as next required to make progress?
Oh gosh, I mean, that's a very political question in a sense, and like one of the people in the chat, I think demand management really has to be thought about in the long term. But of course, there are operational areas that can be improved. I mean, there's an absurdity over the UK where the air traffic management charges mean that some aircraft avoid flying over our airspace. And I think things like that can possibly reduce the climate impact. And of course, the many technological issues that we've heard about, moving to hydrogen. We haven't talked that much about SAF today, but those can all play a part, provided we can generate the fuel at the scale that's needed. And I think that's also a big issue. So those are my few thoughts.
Yeah, no, thank you. Excellent. Rachel, what are your thoughts?
Yes, good question. So in terms of decarbonisation, I think it really is a package of measures. We've talked about some of them today. We need operational measures, technological measures. SAF, of course, is the big one in terms of whatever fuel that is, whether it's electrification, whether it's power to electric, whether it's hydrogen. I think that's where we really need to decarbonise the fuel that we use. In terms of adaptation, I I think we're still at the stage where we really need more awareness raising. I think although more organisations, airports and navigation service providers are starting to engage with the subject, there's still probably quite a big knowledge gap. So, I mean, events like this are really important for putting that knowledge out there and raising that awareness. So I think that that's really important as well.
I think if I could add one thing, there's an increasing number of organisations putting carbon budgets on. Many universities are, and I think that's a very positive thing. And these kind of, as you said at the beginning, Suzanne, these kind of sessions are very important, but they do reduce our carbon footprint. So I think more aggressive ways of restricting how much we fly would be beneficial.
Thank you. Yeah, Tim, over to you.
Yeah, definitely. There's a couple of demand management ones in there. I'd kind of go to the more technical for Keith from Anonymous. So do you have a view that CO2 minimization should be the absolute priority, and how we could activate more rapid ones? Did you see that
Yeah,
one?
okay.
Or thoughts versus
Yes, I saw that one, and actually I realized I finished my presentation one click too short, and had I clicked one further, it would have addressed my opinion on this. And I believe that any mitigation strategy, such as contrail avoidance, that leads to or could lead to an increase in CO2 emissions should be viewed with extreme caution. So almost to the point of being ruled out, because as I say, this persistent nature of CO2 forcing is so serious that that I think some decision has to be made about whether, in any circumstances, emitting more CO2 is a sensible amount. Of course, you can use the metrics to decide whether it's beneficial or not, but then there has to be a proper understanding of what these different metrics mean, and agreement across the sector on what are going to be avoided. But my personal opinion is we should avoid anything that leads to more CO2 emissions.
Right, thank you. Shall I follow up with another question? I apologize. It's the rising sun in Europe is making me rather pitchy, but
yeah, I have the same.
You've got the same. That's right. We're in the same boat. Anyway, last week at the webinar, we had a presentation on reporting and finance, and I just wanted to both of you, like, there's an increasing expectation for companies to report on their climate risk, and so that's the physical risk, but the transition risk, I believe, Keith, airlines are also increasingly asked to report on non-CO2 impacts, and having listened to you, this seems a very difficult task. So if either of you can comment on, I guess, the benefits of those reporting expectations or regulations, but also maybe the complexities. Rachel, if you want to start.
Yes, good question. So, of course, in Europe, some of you may be aware, as part of the EU emissions trading scheme, there is a new requirement being introduced for airlines to report on non-CO2 emissions. It is, of course, it has benefits and disbenefits, as does any policy, I suppose. But I think part of the intention also is to gather information and gather data through the reporting that can then aid scientific research into how to reduce emissions. So I think if it's just in terms of reporting, and I understand that models are being made available to support it, then there is a benefit, because then that data is available to support research.
Yeah, shall I jump in? Some of the questions, feel free that the speakers have a quick go. They're either quite detailed, or we covered regulation last week, and demand management tourism might come in next week. But I've got a question for both of them about the communication. So you've both got science, you've got contrails and non-CO2, Keith, and you've got adaptation, Rachel. How can we go about communicating some of those sciences and concepts to the policymakers and the public in general? Any thoughts on the science policy gap and communication?
That's an interesting question. I mean, within the UK, I mean, on the policy level, I think there's a lot of engagement from policymakers. Of course, that doesn't always translate to decisions, but I'm fairly happy with this. In terms of public, well, I think we just continue having to use the same channels. I mean, this is one example where we're reaching a broader audience. I guess one of the issues is the cross-disciplinary nature of this area, and I think we should be careful about claiming expertise in areas of the subject that aren't our specialist areas. I mean, I in a way, I got sucked into it before. One of Suzanne's questions about CO2, demand management and things, is that that's not my speciality, and so I should be cautious about presenting it, because I think a lot of it's not quite disinformation, but inaccurate information can come from people drifting out of their area of expertise, and that's what personally what I've experienced in this whole contrail avoidance debate is people who weren't specialists making comments that are plain absurd. So yeah, I think recognizing the limitations of our speciality.
Yeah, good point. Very good point. Yeah.
Rachel,
yeah, good. You got anything?
Yeah, I was going to say more events like this. I think these sort of events are a really good way to get information across, because you do get such a broad range of participants, and they are available for people to watch afterwards. But also perhaps as a sector, we need to engage more directly with policymakers and have those really quite frank discussions about what's needed. I think it usually boils down to funding, which is always a challenging topic. But there is, as you said, there can be this science policy gap that needs to be bridged. And I think that is quite challenging, but trying to engage with the policymakers is probably the way forward.
Yeah. We heard about hydrogen in our first presentation, and I would like to pick this up with both of you. One cave around what are the atmospheric effects of hydrogen? That's one thing. And Rachel, for you, because Alejandro showed us various infrastructure investments that might be needed at airports, and how can we future-proof those? So maybe, Keith, if you share with us your thoughts on hydrogen fuel.
Yeah, okay. There's two different aspects of hydrogen. One is the use of hydrogen, and one is the leakage of hydrogen in the chain from production to being used. So there's a lot of research going on the effects of hydrogen leaking into the atmosphere. Now, hydrogen doesn't directly impact the climate, but what it does is have an impact on, for example, changes the lifetime of methane in a way that methane lasts longer in the atmosphere, and a number of other effects. So it's clear that any leakage of hydrogen is undesirable, but at the kind of leakage rates that industry believe are likely, there's no doubt that hydrogen is better than using fossil fuels. I mean, I don't love GWPs, but the GWP has been surprisingly, the studies that have looked at it have been surprisingly well in agreement, and it shows that switching from the hydrogen leakage issue probably is the huge issue. So then we move on to actually using the hydrogen, and of course Alessandro said there's two ways that hydrogen get used in aircraft. If it's used in a fuel cell, then there are no NOx emissions, but there would still be contrails. The jury's still a little bit out about those contrails, but the consensus is that the contrail radiative forcing from hydrogen aircraft would be 20–30% lower. So certainly no worse than present day contrails, but there would be no NOx. If it's combustion of hydrogen, then you would generate NOx. So it's one of the issues here is whether you use fuel cells or combustion. Now with SAF, the NOx issue is the same as really with conventional fuels, but it's also now believed that we now have atmospheric measurements which are more convincing than model estimates, and estimates from the laboratory, which show that again the contrail radiative forcing is likely to be reduced 20%ish, so not dramatically, but still somewhat. So it certainly wouldn't make things worse using SAF. Yeah.
Thank you. Rachel.
Yes, so really good question. So we're talking about adapting our aviation system for impacts that we're going to see in 20, 30 years' time. But do we actually understand what our aviation system is going to look like in 20, 30 years' time? So I think sometimes when we're looking at this, we're basing adaptation planning and decisions on the aviation system as it is today. But it's like I think I mentioned earlier, we're going to have increasing traffic demand. We're also potentially going to have a very different aviation system with hydrogen aircraft, electric aircraft. So how do we climate proof and future proof the hydrogen infrastructure and the electric infrastructure for future climate change impacts? I think is what we really need to be thinking about, as much as how we climate proof or future proof the aviation infrastructure of today. And the other one possibly to think about, we're going to see, we think, an increasing number of advanced air mobility vehicles, potentially remotely piloted unmanned air system vehicles. And how are those aircraft going to be able to operate in a future climate? They're potentially going to be small, lightweight, electrified, so vulnerable to storms, higher temperatures. So I think we need to start feeding this into our discussions of adaptation as well. So what is future traffic demand going to be like, and what is the future air system, aviation system going to look like? So that's a really good question.
Yeah, actually, and before Tim, you might have one more question, but I might even challenge ourselves to say the future mobility system, because someone put a question on if people might want to fly slower. Well, then we've got high-speed trains, you know, so maybe it's thinking how people get from A to B, and does it have to be by air, or what's a hybrid system? So I think you're absolutely right to think outside the box for the future within the net zero climate goals. Tim, we have probably time for one quick question.
Really quick. I think Keith's technology readiness levels, I haven't seen them for a while. What do we need to do next? What in kind of one or two sentences from both of you, what do we need to do next in your area, quickly and succinctly?
Loads of things, but I think predicting regions of predicting ice supersaturated regions in the atmosphere is right at the beginning of the chain of contrail avoidance, and unless we can sort that out, I don't think we'll get anywhere, to be honest.
Yeah.
Reliably.
Yeah. Rachel, any quick, short, sharp
answers? Very, very quickly, more awareness raising, organisations to carry out climate change risk assessments, and then start adaptation planning and resilience, in a nutshell. Yeah,
no, that's great. Somebody, thank you both very much. Over to you, Suzanne.
Yeah, thank you. It's been an absolutely fascinating session, I must say. I've learned a lot, actually. I really enjoyed all three presentations, and hopefully the audience did too, and hopefully our speakers found it rewarding as well. So next week we have our final one for the year, which is the social license to fly. I think this was already alluded a lot in our chats today, but so next week we have time to discuss in more detail how we can maximize the benefits of aviation while still achieving the low carbon transition. So hopefully you can join us next week. If you have feedback for us, please get in touch. And if you want to recommend the session, it will be online next week, as are all our other sessions from previous years. So with that, I would like to thank, all three speakers, Keith, Rachel, and Alejandro, for your effort and for your contribution. And with that, we wrap it up for today. So thank you, everyone, and have a good afternoon, day, or night. Goodbye.